Hello, friends. Welcome to the Nexus Podcast. I'm your host, James Dice. Each week, I fire questions at the leaders of the smart buildings industry to try to figure out where we're headed and how we can get there faster without all the marketing fluff. I'm pushing my learning to the limit, and I'm so glad to have you here following along. Episode 65 is a conversation with Troy Harvey, CEO of PassiveLogic. This is Troy and I's second podcast episode together, so check out episode 5 if you haven't yet. It's from mid-2020. Troy gave me an update this time on where PassiveLogic is in their journey after raising a Series A and more than quadrupling their headcount. Then we took a deep dive into digital twins, the quantum digital twin standard, how it relates to other ontology efforts, why it's needed, what it enables, what types of AI it's using, and more. Without further ado, please enjoy Nexus Podcast episode 65. All right. Hello, Troy. Welcome back to the Nexus Podcast. So happy to have you. Can you reintroduce yourself for those that haven't met you before?
Sure, James, and I appreciate you having me back. Yeah, I'm the CEO of PassiveLogic. We're based in Salt Lake City area. So we have people operating all over the world.
Yeah, and we did episode 5, I believe it was. So we'll put links in the show notes to that. And I've done several different newsletter updates on the company over the past year and a half or so. So put those in the show notes as well. How about you just start with an update on PassiveLogic? So since I think it was last May that the episode 5 came out. So what's been new since then?
Yeah, I think, just to remind, maybe your audience is, I think what PassiveLogic is uniquely, going after is we see this opportunity to really change the way automation and more broadly autonomy, how that works in a generalized sense. And when we talked last, I think we were pre our Series A raise. And since then, we've raised a Series A with a lot of lead investors and strategic investors that are well known in the industry. We have really grown our team quite a lot. So we've probably 5 times our team staff and really been building more deeply in our stack. And we operate at the compiler level where we're innovating a whole new compiler technologies and language technologies at the heterogeneous neural net level, new technologies in AI around, and that's at this deep physics level and at the product level. And so we've really been building out that team. We've had a lot of really great folks come in from Google Brain and Facebook who have joined the team. We recently had a guy who's leading cloud, who was leading Walmart's cloud infrastructure, and really kind of putting together the team that we think is going to finalize this technology but bring it to market as we're working with strategics over the last year on those goals. So that's a little bit of an update of where we are and what we're working on. Yeah,
and those in the Nexus community have seen there's been several members of Nexus Pro who have gone over to PassiveLogic. Do you want to share any of the hires that you've announced, or are there too many to?
Yeah, I mean, sure. Most recently, just today, we announced Larry Weber, who was the general manager of JCI's Asia Pacific region, and prior to that, general manager of Honeywell's Flow Controls. Mike Luscombe's leading commercialization. He came over from Tritium. On the tech side, Kevin Vigor came from Facebook. This is like a total superstar. Brad Larson, who came from Google Brain. He's guys driving all of our differentiable programming technologies at the compiler level and really building up some of the open source technology we're working on. Jay Heron, who many people in the community might know, came to us 6 months ago, and he's driving our quantum API. And Corey, you and he know one another and have worked at Inrail prior, so yeah.
Totally. Well, cool. So today, what I'd like to do is dig into you mentioned the quantum API, dig into the quantum digital twin standard. So on the podcast, I've talked to Corey about Haystack. I've talked to others about other ontologies. This would be fun to unpack. You guys announced quantum, I don't know what it was, 6 months ago, maybe it was last year, even kind of unpack what it is and sort of how you see the world changing with it. So I guess first, we should talk about what digital twin is in your mind, because we've also had a lot of episodes around what is a digital twin. I think if I could maybe compile all the what is a digital twin answers and like turn them into their own episode. How do you see the answer to that question?
Yeah, I think there's some evolution that happens here early in technologies as people are trying to sort out what terminology means, and sometimes they're not even really related, but they're terminology that are easy for people to grasp. What is digital twin? We used to speak in more academic terms when we early on got going, and realized for us, digital twin was very descriptive for people. But at the same time, I think it's gotten a little muddy as people are talking about digital twin in their own framework, right? So I'd say, when I look broadly at the industry, I see most of the things people are calling digital twins, I would say best are described as BIM, or building information management, wrapped into sort of more of a cloud description language, and analytics. So where you take, maybe CAD for building and you're attaching data points to the building. I guess, there's a bunch of things you can ask. Is that just BIM, or is it actually, formulating something new that we might call digital twin? I think there's also a market question: is this just analytics replayed? And I think we all understand how the market around analytics had some challenges, that it's like a little bit, so what? Like you have analytics through a lot of work. Now you need somebody to interpret it. Is that enough? Is that meaningful, right? So I think there's a little bit that we could dig into as a marketplace on, what's important, what do we have to accomplish as a community. But what we mean as digital twin is literally a digital twin, and we think you have to have some fundamentals of what we would call the word ontology. What does that mean? And for us, it's the physics of what things are. And so this describes what it is, who it is, what something's purpose in the universe is, as opposed to maybe how I say it, or some analytics, or some description. And we can get a little bit deeper on what that actually means. But I think when you unpack it, it's really distinct. And I guess the last thing I'll just, state this is ontology is really related notion to digital twin. And the root meaning of ontology is really an existential term. It was developed by the existential philosophers to say, like, what is your purpose? What's my purpose in the universe? And this has been adopted by AI and machine learning people to say, well, what is technological purpose? And we see that very explicit ontology formulation of digital twin is that every entity, whether that's a pump or a fan or a boiler or a wall or a person, they have a fundamental purpose in the universe, and they have a fundamental way in which they connect to the universe, the other equipment around them. And that it's really the question of who am I in the universe? What do I do? As opposed to where ontology is used in semantic purposes to talk about semantic ontologies of, how do I describe things with words?
All right. So back on the digital twin piece, I think one thing that you're getting at here is like, we need another level here of a definition to get at like solving true problems. Is that kind of what I'm hearing? Whereas like,
yeah, I think that's right. I think, we've kind of promoted that our industry needs to get aligned around some common terminology. We promoted a notion of levels of autonomy for this reason, that we need to come into a conversation knowing what we're talking about. Are we talking about a level 1 like autonomy topic? We're talking about a level 5 autonomy topic. And for us, what we see is, where do we need to be as an industry, next year, in 5 years, 10 years, as opposed to, say, a lot of the activities that I see in the industry are kind of rear view mirror activities of, like, given what's happened in the past, how do we collect up all of that into maybe a semantic that we can describe it? Well, that doesn't necessarily get us to where we need to go.
Totally. Okay. So where do we need to go? And how does quantum help us get there?
So there's a couple of pieces to where do we need to go. I'm going to pull back from the buildings market for a moment. I think, everybody's familiar with fully autonomous vehicles. what we basically need across the industry is generalized autonomy. And everybody in whatever automation project you have, your project is some form of autonomy. And often there's things that are unexpected or unique to that project that may not even be considered classical building automation. Maybe you're asked to tie into a manufacturing system, or what about your logistics systems in a warehouse where you're carrying boxes across conveyor belts onto robotic shelves, or an IoT network that's trying to frame how everything in a space like comes together with one unified point of view. So these kinds of problem sets were never going to be solved by how automation's been done in the past programmatically. But as we probably talked before, the biggest realization I think for the industry is, and I was just having this conversation with Larry, there are projects that any big integrator is going to have that are on the order of 500,000 IO points on the large side. 500,000 IO points, just like take that into context for a moment. That is way outscale anything that anybody automates outside the building industry. You go to industrial robotics, you're talking about tens of points. To autonomous vehicles, you're talking about like dozens of points, right? 500,000 points. So once you realize the scale of that problem and why buildings don't work, you need to solve it with something new, right? You need to solve it with something that can actually bring true autonomy to that system to be able to deal with the complexity in real time and not expect somebody's going to be able to digest that in one setting at one commissioning stage, because it's not possible. We know it's not possible.
So can you kind of define generalized autonomy real quick?
I think generalized autonomy. Yeah, so I think where you need to go for just not only the building sector, but all industrial control. If you first frame what is, say, an autonomous vehicle, what's the shape of that? And it speaks to what is the shape of AI and deep learning today. And it's monolithic, right? So what happens if you're an autonomous vehicle manufacturer is you're training up millions of miles of cars and you're looking under different scenarios and you're training one neural net that is monolithically does this one thing, which fundamentally is actually kind of simple, right? You're going to steer, brake, and accelerate. This is not that conceptually that hard. Vision's a problem, but that is monolithic. There's no way to pull steering out. There's no way to pull braking out, right? It's all one thing. Mm-hmm. And so when we look at the future of how do we make all systems autonomous, it needs to be compositional. It needs to be in the hands of the average user that they can say, well, I'm going to take this piece and connect it to that piece, connect it to this other piece. And once I've connected all the pieces together, the system knows what each of those pieces are, how they work together, and how to control that. Mm-hmm. And that's not a buildings problem, that's an everything problem. And to do that, you need some new foundations in AI, because deep learning won't get you to that compositional type of AI scenario that you can, as an average user, can shape the AI yourself and generate that platform for whatever problem it is you're solving for. And so that's generalized autonomy, is how do you make a system able to autonomously control any kind of system, doesn't matter what it is, or any kind of combined set of systems that are interacting with one another. And then how do you make that accessible to the average user?
Do you want to introduce the quantum standard? What?
Yeah, let's talk about that. So what was missing for us in order to, as an autonomous systems company, we had to have an autonomous system description language. And we built Quantum in V1 several years ago. And this bringing quantum to a public spotlight so that it's not just PassiveLogic, it's its own standard, backed by Department of Energy, backed by a bunch of strategic partners that we'll be announcing here in the next few months, is first to power an autonomous platform. So that's its first goal, is you need a description language for this generalized autonomy in order to make that work. Okay. But it then has these other really important attributes. One, it's the first real fully descriptive language of a building. And that means everything in and around that building, whether you're talking about the building itself, the IT systems that are, That's your networking infrastructure. It could be your logistics systems or manufacturing systems, your HVAC systems, your light, all that information in its fully interconnected, real, how its physics actually works as an interconnected whole. So that solves how do we describe buildings as a whole? And then that solves another really key piece is how do we provide an API for buildings? Because there's never really been an API for buildings. And this is an impediment to every single corporation, every startup in the space, every investor who's looking at this space is like, holy crap, the most trivial things require, let's go back to something as simple as comfy back in the day where you had warm or colder, 2 buttons, that started as like $25,000 per building integrations. And that's the problem for the whole industry. If you don't provide a real API, you're never going to solve how do we get these services plugged into buildings. So those are some of the fundamental pieces, but there's some things we can break down about quantum in it has a lot of faces that go into how do you think about like networking of all these devices, how does everything interconnect?
Totally. Well, I want to ask you about the API piece. Sounds like Jay, my friend Jay, is working on that. What separates the API? Well, I mean, obviously, besides the huge integration costs that would be removed, what are the keys to building this first sort of unified API for buildings?
Yeah, so really, when you think about, okay, to get a PassiveLogic control off the grounds, you need quantum to describe it to make it operate. We can talk about how that gets set up and why that's a really powerful thing for the marketplace. So then maybe let's step back. So what you need is 2 things, right? We have all this complexity in the industry, and we've got to make that controllable and automatable and make systems autonomous enough that they can do it in real time to solve the real problems. On the other hand, you also need this to be simple. You need to be democratizable, and you need to get it out into the hands of not just the biggest, baddest programmers and the best integrators in the world, but we need to get in the hands of the average guys on the ground. So one of the key pieces that quantum does is it describes what things are. And that physicality is exactly what our heroes here at PassiveLogic, our Boiler Bob and HVAC Harry, these heroes, they understand, they may not be programmers, but they understand how the boiler is connected to the buffer tank, and the buffer tank's connected to a pump, and that's connected to distribution and the chiller plant and the VAVs, and they understand those things. So now having the description language of what things are makes it so that Boiler Bob, our hero, can go and draw and make that just a diagram like he normally does. And what he's done in that process is describe what is actually the AI for the system for it to control. That description now provides this API by its nature of it is this, what we would call a compute graph or a data graph of the building, so that you could walk from the campus level to the building level, to the floor level, to the zone level, to the sensor, or to the pump, to all the variables in the pump, whether or not those variables are exposed through, say, BACnet or something else, they still exist. And that bringing all the data in a navigable way that's unified building to building makes it so now you can build applications once, and every building becomes just a one click. You just add it from our app store, and you don't have to like integrate with each new building as a different entity.
Very cool. It sounds like it's also more than other description languages or ontologies, whatever we want to use. It sounds like it's describing more about the building than these other efforts.
Yeah. So, I mean, why do we need this, I guess, is a good question. So we have some initiatives to work together on the different existing semantics. Like, we're happy to see things like haystack bloom because that provides more labeling if people can embed that labeling. At the same time, we are working on embedding quantum, right, in like a full quantum description. Let's talk about like what the differences are here, why they're compatible, why they work together, and why you need both. So what I would say is, first, the existing semantics that we have, primarily haystack, I think a brick is in that orbit as well. They're meant to do something very different. And they kind of emerged out of, you start with BACnet or something like BACnet, KNX, whatever. And you have a very low level description here. I've got a point, it might be analog. That's all I know about it. It's not enough. Let's put a label on top of it that that point has a certain meaning. So that's a labeling process, and labeling in AI is helpful because we now know what things are. We don't have to discover what they are. But that just says in some linguistic terms what it is. It doesn't say who it is, why it is, what it is. Like it's just a little bit of language. And so I often use the example of, to separate these concepts. BACnet's at this low level of the protocol, the bits of the protocol, the atoms of the protocol. Haystack or brick would add this next level of labeling. And then what we're doing is adding what is this, true ontology, this like existential piece. And if you put this in robotic terms, if I had a robot navigating around my office, that bottom level is kind of like the robot navigating with its sensors to know, hey, I'm not going to bounce off any walls. And it's like navigating around the building without running into things. Mm-hmm. The next level up is you have cameras, and you can say, hey, that's a door, that's a window, that's a person, that's a dog, that's a file cabinet. So now things are labeled, but you still don't know what a door is, right? Like that, a door doesn't tell you anything. So the existential nature of the door is actually a router. A door allows you to route from one room to the next room, and it has some physicality that it swings on hinges, and that physicality is the fundamental description of what a door functionally is. And so that's where I'd say this differentiation is between what quantum does, is it describes that existential piece that is missing from just the labeling piece. Now, it turns out if you have the existential piece, it's often easy to work back to the labels, but the labels can feed into the existential piece to help inform what things are at commissioning time.
So where do you see all of these like long-term, we have all these separate efforts, right? Where do you see them going? Do you see a convergence? Do you see them just like being translated automatically between each other by some other middle tool? How do you see this going with all the different efforts out there?
Yeah, well, what I see is the remarkable amount of excitement we get from large entities in the equipment and in the building space on quantum to solve their overall problems. But that's not incompatible with making BACnet smarter. That making BACnet smarter will always make things easier. So efforts like 223, that's the right thing to be doing. Haystack, the more people like do labeling or embed quantum, the better off everybody is. So the thing that quantum does that is different, what we're not looking to do is invent another standard for semantics. There's plenty of those. What we're looking is that meta piece that is the singular, like what is thing ontology that you can connect all those into. And the more you have, the richer it becomes. And so it really doesn't matter which things, does Matter start taking a pole position, start moving into commercial? Great, that gives us more information. Is Haystack gonna do that? Great, that gives us more information. Are we gonna see more direct embedment of quantum? Well, terrific, we have the full description. But all of those efforts can work together under the singular umbrella of bringing that into a singular, like well-descriptive ontology of the existentials of what things are. Is that too abstract? I mean, we can kind of try to break down like that abstraction of like the existential what things are if it's not
I'll see if anyone reaches out to me, but I feel like I get it with the robot example. I feel like that was helpful.
Hey guys, just another quick note from our sponsor, Nexus Labs, and then we'll get back to the show. This episode is brought to you by Nexus Foundations, our introductory course on the smart buildings industry. If you're new to the industry, this course is for you. If you're an industry vet but want to understand how technology is changing things, this course is also for you. The alumni are raving about the content, which they say pulls it all together, and they also loved getting to meet the other students on the weekly Zoom calls and in the private chat room. You can find out more about the course at courses.nexuslabs.online. All right, back to the interview.
You mentioned embedding this into devices. I have struggled with, following Haystack and following others in that there hasn't been enough adoption from device manufacturers in self-describing using these standards. I don't want to throw Siemens under the bus, but like Siemens is very active in the Haystack community, sponsoring everything, doing all this. But how many of their devices actually self-describe using the Haystack standard?
Right.
I'm sorry, but there aren't very many. Like if you go to the branch office in my local market, they're probably not using it. So what do you mean by these partnerships that are growing where they're embedding quantum into their devices? Is that what you mean?
Yeah. So let's talk about on three levels on how quantum is powerful and effective for the end user, regardless of whether or not they embed it.
Okay.
So first, with quantum, when you're on your Hive and you're in Autonomy Studio and you're drag and dropping your different parts into your diagram, we know what those parts are right in the Hive. So it owns who something is as a proxy. So a device doesn't need to know their quantum model on their own, because what you're doing is defining, hey, that's a pump or a valve at the point that you've dragged and dropped it. And now when we go connect out to it, we know that we're connecting to a pump. And if that pump is just backnet, well, we can get you partway there. You're gonna have to do some of the visual wiring of the points yourself. If it has Haystack, that can help it further so that we can automatically wire up more in the commissioning phase. If it has quantum, it can fully describe itself and a little bit more detail that it's not just a pump, but and we can have, with our manufacturer partners, we're gonna have a very rich library of manufacturer models. So not just a pump, but manufacturer A's pump with model XYZ. Still, we're proxying that for the pump. But if we ask that pump who it is, it can have a quantum model, not for its manufacturer model, but for that exact pump as it came off the validation of their manufacturing line. So it provides a level of detail and information that wouldn't otherwise be feasible. So first, I just want to set that aside because I think that's an important difference here. To PassiveLogic, it's not crucial that it's embedded.
Yeah.
We can proxy those things, and we make the dumb sensors and the dumb controls the equivalent of smart sensors and IoT devices just by proxy. But when it comes to why would a manufacturer want to embed quantum, first, you got to understand that quantum actually solves problems at the point of manufacture. What we just talked about is you have unique information per device that's coming off the assembly line that you need to store. And this gives a common format that's solving problems at manufacturing, that then solves problems at configuration and control, that then solves problems at runtime. And so that whole arc of how does quantum help you in your ecosystem as a device manufacturer is very unique to what quantum. The other reason, I guess, that I would say that we're seeing uptake here is a couple of things. One, I think most manufacturers have come to this realization that they're maybe coming to the end of how much innovation they can have within the shape of just their one component that they sell. They've maybe innovated that to a point that they're not that differentiated from their competitors. So what makes them differentiated is how well they work with controls. And with PassiveLogic really leading that market edge of this is the future of controls, there's a lot of reasons why manufacturers want to regress to that point. Right?
Yeah.
And I'd say Haystack had a little bit at the same, there was other efforts similar to Haystack that didn't go anywhere. Why did people start using Haystack? Well, they had a killer application for it, right? It was SkySpark.
Yeah.
So we have a killer application for quantum, and that's the PassiveLogic, control ecosystem, how to control it.
Totally. Very cool. So can you talk a little bit about the kind of the for the ontology nerds out there, what are the new concepts that quantum brings to the ontology effort?
Yeah, so beyond being a fully descriptive ontology of everything, the building and everything in and around it, we bring these new concepts that are really crucial to how autonomy has to work and how this new type of AI we've been working on functions. And that's actors, quanta, and behaviors. Those are the three key pieces. And there's two subtler pieces that are similar to what people have experienced before, particularly properties. That's more similar to other semantics. We focus on this on the physicality there, and then computed properties. But I'll focus on those top three because they're really important to this new kind of AI that we call typed AI or heterogeneous neural nets.
Okay.
So first, we spend a lot of time looking at all the equipment in all systems, not just building systems, but logistics systems, IT systems, manufacturing systems, process control. And we found that there were actually only 9 actors in the universe of systems. And this was somewhat surprising that there are only 9 roles that things play. For instance, a transport transports a quanta, and we'll get to quanta in a minute, but its job is to transfer a quanta from one place to another. So that could be a pump moving water, or a fan moving air, or a conveyor belt moving boxes. A router, we talked about a moment ago about a door is a router. It routes from one room to another. Well, that's the same notion as a valve routing water from one part of a hydraulic system to another, or a damper in an air system, or a literal IT router that just routes network traffic. Those are all doing the same job. So this notion of actor is really important to solve a key thing that quantum has to solve as this existential ontology, which is, who am I? So we often in semantics talk about like, well, I've got a machine to person, communication. Then I need things to be more machine readable, and things like Haystack try to be more human readable. So it makes sense. You have machine to machine communication. There's a few projects like that, like 1M, 2M that tries to solve machine to machine. But there's this fundamental thing. If you're going to have autonomy, you need a machine to self. Like, who am I, right? If you can't solve who am I, you can never control yourself. And so actors are a really important notion of who am I? What's my job in the universe? And its counterpart is quanta. What is the thing that's the currency that actors act upon? Okay. And it turns out, again, there's a limited set of currencies. And so fluid quanta are one quanta, mechanical quanta. Now these have subtypes, like fluid quanta could be phase change material, it could be water, it could be air. Those are all different kinds of fluid quanta. A mechanical quanta could be a translational mechanical quanta, or rotational, or a 2D vehicle. These are all like, how do I interact with, my actor? What does it do with the substance that it's the currency between actors? Mm-hmm. So these two concepts on the high level are required for understanding yourself to autonomously control. On the low level is the foundation for a new kind of AI called typed or heterogeneous neural nets. And it solves this problem, which is, we talked moments ago about that AI has tended to be monolithic. You train a car to drive, it only knows about driving a car, and there's no way to tear out just the steering from that and then compose things together. Well, quanta are the types by which actors connect to each other. That means you can develop your own digital twin for a valve, and I can develop my own digital twin for a pump. Both of those have the quanta of a liquid, and they just connect together. And I don't need to learn about a pump and a valve together as a whole new entity. They can compose themselves in real time. So now this enables people to make their own custom autonomous systems and gives you that generalized autonomy at the AI level that now, because of types or because of quanta interfaces, you have this composability of different fragments of model. Does that generally read?
Yeah, I mean, makes sense to me.
So then there's one other piece there that we didn't cover, which is behaviors.
Okay.
So an actor, if you're for instance, let's say you are a transport actor, you will have a certain set of required behaviors that you have to fulfill. And so when somebody's making their own digital twin, you're saying, okay, this is an actor that I'm making a pump. It is a transport actor with a fluid or subtype liquid quanta. Well, that has certain behavior requirements that you're going to have to fulfill that will then fulfill what fluid quanta need to know in order to move and understand pressure and flow and all that stuff. So behaviors are then these sort of known notions, and I'll take a simple one, resistance. A resistance behavior would be pretty much any hydronic or liquid actor is going to have to fulfill the resistance behavior. Well, the resistance behavior is also true of any other kind of energy type quanta. So in the energy type quantas, you have mechanical quanta, you have energy quanta, you have liquid quanta, and you're fulfilling that so that it's true for the autonomous system that I don't really have to care about the details at many levels of how you work. Resistance in a meta way across all of these different types of systems. And so what you're doing is you're providing these higher level notions of behaviors of this. When we're talking about like that robot again, the robot has behaviors. It's going to have the behavior, let's say, opening that door that is a router. And that opening behavior is a behavior on the robot that you can fulfill what that behavior is. So these three concepts are really new to not just the building space, but ontologies in general. How do you build AI and generalized autonomy on top of these core notions of what things are existentially?
Cool. And then I guess my question then is then how, maybe we could just bring it home and like revisit the levels of autonomy, like where does that get us now that we can describe a building in that way? We're now allowed to do what? Maybe kind of like wrapping a bow on the
yeah. So let's kind of like talk about where the industry is today. So the vast majority of everything we see out there is this level 1 autonomy, where it's just manual control. We're doing PID, we're doing set points. That's all like hand programmed. You see a few efforts. There's probably a half a dozen companies in what I'd call level 1 autonomy. This is same dumb control in the building, same PID, same set points. You put some kind of machine learning, AI on top, whether it's local or in the cloud, that's just tweaking and tuning the variables of dumb control.
Yeah.
We believe just going through the set of logic that it's not possible to get that stack of technology to level 2 autonomy and sort of breaking these down. So I think, like let's go to the top and sort of work backwards. So level 5 autonomy is fully autonomous. The building is making its own control decisions, meaning you are coming out with, however you want to frame that, your own sequences in real time. There's no pre-canned. You're saying for this given moment, what's happening in this building, all the inputs that I see, am I able to generate a sequence? That generation of sequence is really the fulfillment of level 4 autonomy of like, can you generate sequences relative? So you're basically saying this is the path to take. Mm-hmm. The level 5 autonomy is, can you bring it all together as a bow where I am taking all of the systems in coordination and the building, solving it as a whole system and coming up with the sequences for all of that fully autonomously. There's no assistance, there's no human assistance in the loop. And so this takes us to that point of pure, true autonomy, and not just in buildings, but it could be, again, a process control or manufacturing or whatever kind of system that you have to manage. We've built on top of that level 1 through 5, where we see the building industry has more opportunity, where the system can do even more than just run itself, but help guide its own install, help guide its own commissioning. And those are also these interesting outcomes of this approach, is that by definition, if you define the system, now you can then guide the person through the install because you know what the system's supposed to look like, and you can look at the diffs or the deltas of how the system the reality doesn't match the design. And that's true for commissioning as well. And so it sort of unlocks these other steps as well.
Got it.
Does that make sense?
Yeah. And I've seen the levels before as well. So that I think those were 6 and 7, those 2 that are added on top.
Those 6 and 7.
Okay.
Yeah.
Cool.
And I think, look, that's our proposal for industry. I think as industry, this should be an active conversation. Mm-hmm. And I'd love to see industry come together and settle down like, hey, we all agree on this, so that we're not just like digital twin, AI, like that people are talking about real things.
Yeah. Do you guys get any feedback? I'd imagine that most people aren't thinking at that level, and therefore you're not getting a lot of feedback. But what's your experience been?
No, I mean, yeah, one, in this industry, I think most people aren't thinking at that level, and most people are just like, PassiveLogic solves all these problems. That's really awesome, and they don't really see anything else in that category. But I think as we see more things emerge in the marketplace, and we certainly will, we should have a framework for talk about it clearly, because at the high level, if we're talking on investors or we're talking, in ASH rate conferences, we should have some specificity to, what are the experts talking about?
Cool. So there's a couple concepts that you've talked about that I want to make sure I understand before we move on. One is you've said typed AI. What do you, and we just walked through actors and quanta. What do you mean by typed AI?
Yeah, so when we started this and we said, wow, deep learning is not going to do it. You can do certain things with deep learning, right? You can have dumb controls and you can learn with deep learning some pattern recognition of how to tweak dumb controls to adjust them. But there's no way to get deep learning as it stands to ever control the building. And the key fact here that people should kind of get clear in their mind is one of the big differentiators between cars and almost every other thing that you might want to automate is that almost all the other things are one-off unique projects. There's no duplication, right? So if you're doing cars, you can train that neural net and it's monolithic and you can sell 100,000 of them.
Okay.
But in buildings and factories and all these different scenarios that we have in industrial automation, everyone's kind of one-off. Even the ones that seem like they're patterns, every other customer I talk to is like, I thought I was going to do VRF, and then there's always like this one extra thing, right?
Yeah.
So given that everyone's unique, if you were to take a deep learning approach, you would have to learn on that unique building because deep learning is monolithic. It's not composable. And let's think about how slow buildings are. They take a whole year to go through a cycle of data. To get enough cycles of data that you've got, a good scenario of all the different, situations and states and people activity and weather, you're talking hundreds of years, and that's just not practical, right? Like, I'll commission your building in 100 years. So how do you solve this? So we talked about the composability piece, and that's now built on a new kind of framework for AI. To understand what this is all about, it's important to understand that PassiveLogic, we're literally inventing new language and compiler infrastructure to drive our AI ambitions around our product. And Brad here, who came from Google Brain, is driving quite a good deal of that. And the key piece of information here that is maybe new to most people, even most developers, is differentiable programming. So here's the kind of underlying, sort of breakthroughs is differentiable programming is a way in which you can run code backwards effectively. So I'll make this simple why this matters. For the history of all computer science, there's been what we call timescale problems, or often referred to as intractable problems. We stop short of calling them impossible because they're technically possible. They just may take so much time that's not feasible. Mm-hmm. And I'll give you an example of this, in neural nets, and what unlocked things in deep learning was differentiable programming, which is if I've got a neural net that recognizes cats or whatever thing you're using your deep learning for, you might have 1 million neurons, each with a variable that you can tweak.
Yeah.
If you have 1 million inputs to get an output, is it a cat or not? It turns out trying to find the right tweaking and tuning of 1 million variables is an exponential time problem that may take you thousands of years in the fastest computer. And that time problem is if it takes 1 minute to solve a 1 variable problem, if you have 10 variables, it's 1 minute to the 10th power. If you have 1 million variables, it's 1 minute to the 1,000,000th power, and all of a sudden you're in trouble. And this has held back whole swaths of computer science. There's tons of problems that fit in these categories, these timescale problems.
Okay.
It turns out through a trick of reversing the problem, that's not just the same problem reverse. You're saying, I've got one thing to tweak, and I now get 1 million things out. And you turn what has been an exponential time problem to a flat, constant time problem. And this is what's unlocked deep learning to happen now. It's not because neural nets are new. They've been around for 50 years. But in deep learning, differentiable programming was really kind of a hack because you only had one function in all of the neurons that you were differentiating, which meant what is its derivative function? Well, you only had to define it once. And so that was an easy thing to hack in what we call backpropagate in deep learning. Well, our work over the last couple of years with a couple other actors in the open source community has been to let's generalize differentiable programming. What if every code, chunk of, functions, whatever you're doing, whatever you're writing, everything you wrote, you would automatically get the reverse derivative of that code. Now, all of a sudden, all kinds of things are possible, and it solves a broad swath of CS problems that have hounded people for decades. Well, that's what we've been doing on the compiler level, specifically with the Swift language, work with Apple and Google, and we've been, recently collaborating with MIT. There's a very small handful of compiler engineers who are, really understand how the stuff works down deep. And Swift, we've started really evolving that language because it had some unique features around what we call types, which is like types are that the language itself know what a type like a float or an int is and the relationships to one another as opposed to they're just like hard-coded magic values.
Okay.
So that piece, so that's a little deep, but that piece then allows us now to have generalized differentiable programming. It's no longer linked to deep learning in the simple use case. We can do it in all kinds of use cases. And then we can build quantum on top to describe these types of quanta, these types of vectors, and they can all work with that same machine learning power that we've seen in deep learning, but now with things that actually understand their own physics and their own interfaces to one another. And so that's really like what quantum on the bottom side is really enabling is it is really a description language for the AI and this whole new kind of differentiable programming. So hopefully that was described well enough that it wasn't too deep, but that's like kind of the underlying, technology.
I think I'm going to make it my goal to replay that section back to myself until I understand what you just said.
Our goals aren't to lose all your listeners in the process. What my goal, is really to try to make these deep technology things as tangible to people as possible. And then through our product, at the end of the day, people don't have to worry about that, right? It's all enabled to make it like people, right? Like I tell our team, our job is to make deep AI, turn that into people, right? Like make that peopleable.
Yeah, and certainly like the drag and drop interface. I'm going to put this pump here and this, expansion tank there, and everything happening in the back end. That's certainly understandable of like where you're trying to get to for sure. Can you talk a little bit where you're at with that piece of it as well? So like creating the digital twin, and really I'm also curious around like where you guys are at as far as bringing the product to market. Like where are you at in that cycle of things as well?
Yeah, so all the stuff we just talked about, that's very deep. There's a few players in that. I could have all the differentiable like compiler engineers probably fit them in our conference room worldwide. You go up the stack to quantum, there's a bunch of industry players that we're continuing to work with, and I see that expanding very rapidly over the next year. But again, that's a small community. I think we see that in all of the semantics, and one of the problems with these description languages is they're a little too inaccessible. So the first piece, taking inaccessibility and making it accessible is we're building a piece of software that will be available to our partners in the next month or two called Quantum Creator. That again, its own very easy to use graphical software for building your digital twins. And so this, again, takes it out of the hands of the PhDs, the people who like swing Modelica and Energy Plus around, and puts it in the hands of, what I'd say is more average engineers and technical people. But that's a certain band. Now we've increased what is, often obscure in these semantics to much less obscure. But then how do we get into the millions of people's hands? And that's where Autonomy Studio, our software, I think that we've talked about in the past, really becomes everybody can do this, define their own autonomous system, draw it, and you're good. And that's really your millions of people interface. So we see what we're doing at multiple levels of how do we engage with different audiences all the way up the stack to the point of the Hive controller, which we'll install into your building in this very practical way. That product right now is going into private beta. We'll be going into public beta, beginning next year. And we'll be going into general market sometime next year. As you know, supply chain is kind of everybody's problem right now. So we'll see how supply chain goes, and when that exact release date, we'll certainly let you know when we're going to announce that. In the meantime, though, we will have these other pieces that we're working with strategics on: Quantum Creator, and Autonomy Studio. Cool.
And do I have it? Am I remembering correctly in that you can, when you do go to market, it will either be through a supervisory controller that pulls in the existing stuff, or basically a full stack that you would provide? Is that kind of?
Yes. So PassiveLogic is like an end-to-end solution. So our Hive controller is the core product that has everything we've talked about is down in the engine of that thing, with Autonomy Studio on the screen, and you can run from beginning to end of your project, including the setup, the networking, all of the decision-making, all in the one box as a single point solution. And then you might put 1 or 10 or 100 of those in your building, how big, however number of IO points you have to manage. And then in a retrofit scenario, we'll be talking down backnet to your, tier 2, tier 3, tier 4 type control devices. But we're always that wrap up at the top.
Mm-hmm. And then you mentioned App Store earlier. Is the direction still to be able to plug anybody's software application into the API?
That's right. So we, on the App Store with this Quantum API, we have third-party partners that are going to have their applications. So if people are, startup in the space, we need a certain service that we need to enable, but it's been a real impediment, huge cost hurdles to get into the building. This makes it not only a free market that you can get to a wider audience, but something that you can take away that integration cost. And then for corporate customers, we have a ability to do corporate applications that only appear to you and your team, that allow you to do your corporate integrations to whether analytics solutions or corporate management, costing software, whatever you want to hook in.
Cool. And then I think this is my last question. You mentioned HVAC Harry and Boiler Bob, but you also mentioned the Quantum describing literally everything about the building. Do you foresee expanding beyond HVAC into other siloed systems, traditionally siloed systems in the building, and other sort of use cases and different personas besides those two?
Totally. So that's some of the more exciting partnerships that we've recently signed, are in these domains that haven't been BMS in the past. And in some of them, they're on a cost-sensitive domain. In some areas, it's in industrial domains that just BMS doesn't add value historically. So let's say your problem set is more of an IT networking infrastructure problem set, with some IoT knowledge around that, or the logistics or the industrial or the manufacturing, the process control. This is where I see a lot of exciting, new emerging opportunities, because it's not just the shell of the building. It's not just the systems that make the building go. Of course, buildings are full of things, and those are interacting with the building and the systems. And so it's all one thing. Yeah. And more what we see is people wanting to get that one total view of their building and their business processes.
Totally. Very cool. All right. I think we should, given the depth that we went into, maybe leave this episode here for now. I know we have other topics we want to explore in the future, but sure, maybe we can revisit this again in another episode in a couple months. But thanks for coming on the show again. It's been fun. I always learn a lot every time I talk to you.
Well, I appreciate having me on, and I look forward to talking further.
All right, friends, thanks for listening to this episode of the Nexus Podcast. For more episodes like this, and to get the weekly Nexus newsletter, which, by the way, readers have said is the best way to stay up to date on the future of the smart buildings industry, please subscribe at nexuslabs.online. You can find the show notes for this conversation there as well. Have a great day.